What we're going to talk about today is the start of Unit 4, which is simple harmonic motion and waves. Okay? Simple harmonic motion is any motion that repeats itself over and over again. Okay? We're going to be talking about some of the same variables that we talked about in Unit 3. Okay? Things like period, frequency, okay? Things like that, okay? Because they are also going to apply to periodic motion, okay? Or simple harmonic motion. Okay, so we're going to look at what simple harmonic motion is. We're going to look at how it can happen and be maintained, kind of like what we did on the first day of Unit 3, looking at circular motion, how it happens and is maintained. Okay, and then we're going to look at the two common examples of simple harmonic motion, a mass on a spring and a pendulum. Okay, those are going to be our two examples of simple harmonic motion for this unit. Okay. All right. In case anyone was wondering what the cartoon was. Chickens can't fly anyway, but they can't do anything if they don't have bones. So the next time you have boneless chicken wings, it's just like the pulp from the cutting room floor. All right. Now, if you had any type of, exposure to, let's say the outdoors during your childhood, you probably used a swing set at some point. Okay, you swung back and forth on a playground swing. If that's the case, then you were a pendulum. All right, and you were exhibiting simple harmonic motion, provided you were not pumping. Okay, because we all know if we want to get the pendulum to go higher or the swing to go higher, okay, we have to pump our legs, okay, and put in that extra energy. We're putting tension in the chain and getting us going further. But if you stop pumping, okay, you gradually come down to kind of this little swing where you'll keep oscillating back and forth for quite a while, provided you don't drag your feet. Okay? And you'd swing back and forth through that narrow range, okay, for some time. Simple harmonic motion works very well over a small range, especially for a pendulum. Okay? Now, in order for simple harmonic motion to occur, there has to be a force there to cause it. Okay? The reason being is if you imagine a pendulum swinging back and forth, see how often the ghetto physics demo comes up? It's awesome. Okay? It's useful all the time. Okay? So anytime simple harmonic motion happens, okay, so in this case the pendulum, is the speed of the pendulum changing? It is, right? It's going up, slowing down, stopping, then turning around and coming back. Okay? In order for its velocity to change, there must be a what? What causes accelerations? Forces. Okay? Now, in this unit, the force that causes this to happen is called a restoring force because it is trying to restore equilibrium. Okay? For a pendulum, equilibrium is right here. Okay? Where the mass just hangs straight down where gravity would have it rest. Okay? In order for this to get going, I have to disturb the pendulum. That is, I have to exert a force on it through a distance, pull it away, do some work, give it some potential energy, and then let it go. Okay? So what is acting as the restoring force in this particular situation? Gravity. Yeah, well, I mean, to an extent gravity. It's actually a component of gravity that acts along the arc. Okay? Because one of the things that has to be true for simple harmonic motion to occur is that the restoring force has to vary linearly with how far from equilibrium you get. Does the force of gravity increase? Like if I have this thing hanging here and I move it to here, its weight is still the same. Okay? Gravity doesn't increase as I move it away from equilibrium. But the part of it that acts along the arc does, because the more out here I get, the more directly opposed to gravity it becomes. Okay, so in that case, it is the component that acts along the arc that is the restoring force, and that actually does vary linearly, okay, along the arc. Okay, if we were talking about a mass on a spring, okay, so if I have a spring and I just have a mass sitting on it, okay, and it's horizontal like this, and nobody pushes it, will it just sit there? Okay, but if I push it in so that I compress the spring, the harder I push it, or the further I push it, do I have to push it harder? Okay, if you think back to the spring lab you did with the rubber bands in Science 10, okay, where you put the spring scale on the rubber band and you stretched it out, okay, the further you pulled it, the harder you had to pull. Okay, that is a restoring force varying linearly with displacement. The further away from equilibrium you go, the harder you pull. Okay, everyone all right with that idea? So, playground swing, okay, goes back and forth. Vibrating mass goes back and forth. This red dotted line that you see here, okay, would represent the equilibrium position of the mass on the spring. Okay, for the playground swing, this person here is at the equilibrium position. This person is obviously not. All right, everybody okay with that idea? Okay, guitar string, same thing. Okay, any string instrument, if you pluck the string, does it vibrate back and forth? Okay, that's what makes the sound, right? But if you don't pluck it, wherever it sits is its equilibrium position. Okay, the harder you pluck it, obviously the further it's going to go. Okay, the louder the sound it will make because the amplitude of its motion is greater. Okay, everyone all right with those ideas there? Okay, so simple harmonic motion is related to waves, okay, because it is the simple harmonic motion of a guitar string that causes sound to be produced. Okay, so they're tied together, okay, in that way. Okay, so we talked about this equilibrium position. That is where the object would sit were it not disturbed. Okay, so if it were not disturbed, okay, that is where it would sit. So for this example here, okay, the equilibrium position would probably be right here. Okay, so this thing is going to oscillate back and forth, and as it oscillates back and forth, it will compress the spring, stretch the spring, and go back through equilibrium each time. Okay, everyone all right with that? Okay, what would we call the amount of time it takes for it to make one complete oscillation back and forth? Hertz. How many times it does it per second would be hertz, it would be frequency. What would we call the amount of time it takes to do it once? Period, exactly. Okay, so we're going back to period and frequency. Okay, so equilibrium position, important term. Okay, and anytime you pull it away from the equilibrium position, the system will try to pull it back to equilibrium. It's trying to restore equilibrium. That's why we call it the restoring force. Okay, so that force could be gravity. Okay, it could be the tension in the spring. Right, it could be any number of things. All right. How many times in one oscillation is the object going to go through equilibrium? Two. Okay, if we start here, okay, it's going to go back, then through equilibrium, and then come back again to equilibrium. So it's going to pass the equilibrium position twice in every oscillation. Okay, so this sentence right here is super important. It is the basis of all simple harmonic motion. Okay? If simple harmonic motion is to occur, the restoring force, that force that's trying to bring the object back to equilibrium, has to vary linearly with displacement. So the further from equilibrium it gets, the harder the restoring force will pull it back to equilibrium. Okay. So for the spring, the restoring force is obvious. It's the spring. Okay. The more I stretch a spring or compress a spring, the harder it pulls. Okay. So if I was to push on this mass, okay, in this direction, the spring would push against me directly back towards equilibrium. Okay. If I was to stretch the spring by pulling the mass downwards, then the spring would pull back towards equilibrium. Okay. And that force would increase the further away I got. Okay. With the pendulum, okay, we said we were relying on a component of gravity acting along the arc. So at equilibrium, gravity pulls straight down. In fact, gravity pulls straight down no matter where you are along that arc. And it pulls down with the same amount of force no matter where you are along that arc. Okay? At equilibrium, there's no component of gravity acting along the arc because they're perpendicular. Okay? Gravity is straight down and the object is moving horizontally at the very bottom of the arc. Okay? The further away from equilibrium you get, the combination of gravity and the tension in that string, okay, is going to produce a force that is directed along the arc. Okay? As you get further along the arc, okay, that force is going to get bigger and bigger. Okay? The force that goes along the arc. See how those arrows are getting slightly longer each time? Okay? So it's not gravity that's acting as the restoring force, it's the angular component of it acting along the arc. Okay? Everybody all right with that? Okay. So a mass and a spring can oscillate with simple harmonic motion, so can a pendulum. What things do you suppose would influence the period of a mass on a spring? What could make it take more or less time to make one complete oscillation? Assuming it's horizontal.
The distance.
Okay, so the amplitude? Actually, believe it or not, no. Because the further it goes, the harder it pushes. So it'll actually take the same amount. But you guess, because I mean, it doesn't make sense that it would travel further, but the acceleration and the force become greater. Okay?
The amount of force applied?
Okay, the amount of force applied, same thing. The further I go, though, the harder it's going to pull. So it's going to have still the same amount of force. I'm just looking for how long it takes to make one oscillation. It's a mass and a spring. What two things can affect its period? If I have a spring and I put 1 kilogram on it, it'll oscillate back and forth. If I put 5 kilograms on, it'll oscillate back and forth, but will it take nearly as long? No, it'll oscillate really, really quickly, okay? Because it's got way more mass on it. The less mass, okay? Sorry, I said that backwards. Okay, the greater the mass, the longer the period, because it'll have all that extra momentum, right? It'll just keep going, okay, further and further. With a small mass, it'll just oscillate back and forth. Okay? Are all springs the same? Are some springs stiffer than others? Like if I'm comparing the spring in a clicky ballpoint pen versus the spring in my car, okay, they're different, right? If I hung a 1 kilogram mass off the spring in my car, that spring would hardly move. But if I hung a 1 kilogram mass off the spring in a clicky pen, it would probably just fall right to the floor. Okay? So the two things that can affect the period of a mass on a spring are the mass and the spring. Okay? Or what we call the spring constant, the stiffness of the spring. Okay? So mass is always going to be in kilograms, and this is going to be in newtons per meter. It tells us how many newtons would have to be applied to stretch or compress that spring by 1 meter. Okay, what things could affect the period of a pendulum swinging back and forth? Only two.
The radius or the distance?
Yeah, the length of the pendulum, okay, the distance from the pivot point to the end of the mass. Okay, the long pendulum, okay, goes like this, but if I suddenly shorten that, it swings back and forth a lot quicker, right? Okay, what else? I already heard some people saying mass. Everybody always wants to say mass, but mass actually doesn't affect it. Something maybe related to what you were thinking does. If I did this on the moon, how would it look? Yeah, a lot different. Be a lot slower, because on the moon, what's different? Gravity. Yeah. Okay. The two things that affect the period of a of a pendulum are the length of the pendulum and the acceleration due to gravity. Why doesn't mass affect it? Because of gravity. All things fall at the same rate, regardless of their mass. Okay, but there's a gut reaction that says mass does make a difference. A heavier pendulum will fall faster, but it doesn't. In fact, we're going to do a lab to prove it. Okay, we're going to test amplitude of a pendulum, so how far out we take it. Okay, we're going to test the mass of the pendulum, okay, and the length of the pendulum. All right, we're going to find that only one of those things actually affects the period of a pendulum. Okay. All right. Okay, so the motion of objects with simple harmonic motion can be described with period, okay, and the inverse of period, which is frequency, okay, as well as the amplitude. Okay, amplitude is how far from equilibrium the object goes. Okay. All right, so definitions there: period, time needed to repeat one complete cycle. Okay, and amplitude is the maximum distance the object moves from its equilibrium position. Okay, so in this diagram here, okay, this would be the maximum amplitude, as would this. Okay, the maximum distance from equilibrium. Now, as this motion occurs, okay, if we're at equilibrium right here, okay, how much force is the spring exerting on the mass at equilibrium? None. At equilibrium, the spring is neither stretched nor compressed. Therefore, it isn't exerting any force. As soon as we move away from equilibrium, does the force increase? It does, linearly with displacement. Okay, so what happens is, here at equilibrium, there's no acceleration. Okay, because there's no force. But velocity is actually at its maximum. That's where the object would be going the fastest. Okay, now, as it moves away from equilibrium in this direction, the force is now trying to do what to it? Pull it back towards equilibrium. So what do you suppose is happening to the speed of this object? Yeah, it's slowing down, right? Because it's accelerating back towards equilibrium because that's the direction the force is pushing. Okay? So when we get to our maximum amplitude, speed is 0. And the acceleration of the object, as well as the force on the object, are at their maximum. Okay? As that thing returns to equilibrium, it is accelerated the whole way there by the spring. So when it gets back to equilibrium, we're once again at a maximum velocity, but no acceleration, because once we get to equilibrium, the spring is neither stretched nor compressed. So for something oscillating with simple harmonic motion, it is like an exercise in failure. The restoring force is always trying to restore equilibrium. But every time it gets there, it just goes right on by. Okay? I mean, if we're looking at this pendulum, okay, and it's swinging back and forth, okay, because I disturbed it, it passes right through equilibrium and just keeps right on going in the other direction. Okay? Equilibrium is never permanently restored. It just passes right through it, okay, and then makes it do the opposite thing on the other side. Okay? So, as we move up from equilibrium, okay, once again, our acceleration and force increase, our speed decreases, because our restoring force is trying to push the object back to equilibrium. Okay, when we get back to equilibrium, we're back at our maximum speed with no force and no acceleration. Okay, so we could watch the force go up and down, up and down, up and down as this thing oscillates.
If you were like in space where there's no air resistance or gravity and you like pump the guitar, would it vibrate like forever?
No. because it's not just about air resistance that slows down a guitar string, there's internal friction within the guitar itself, right? Like the attachment points, okay, are gonna push it against like the bridge. Is that what it's called? I can never remember the parts of a guitar. Okay, but anywhere where it's like physically attached, there's gonna be some friction there. Okay, with no air, yeah, it would probably vibrate for longer, but you wouldn't get to enjoy it, because without any air, it also isn't gonna make any sound, right? So you could hit the guitar and just nothing. Okay, the strings will vibrate, but that's it.
If you had like a pendulum though, in a, like a theoretical room where the only force that is able to act on this pendulum is gravity, like no like friction, there's no air resistance, would it go forever?
Yep, 100% would go forever. Okay, and this is why we use pendulums to keep time for so long. Okay, if you could make the pivot point pretty reasonably low friction, okay, you could get a pendulum to keep accurate time for, you know, most of a day, provided, what did you always have to do to an old grandfather clock? Anybody know? You had to wind it up. Okay? They usually had like a little keyhole in the face, okay? And you put the key in there and you turn the key, and what you would do is you would compress a spring in there that was actually attached to the pivot point. And so throughout the day, it would provide just a little extra force on each swing to make sure that the pendulum always swung through that correct angle. Okay? So a grandfather clock back in the day when they were big, okay, you know, was a pretty reasonably accurate way to keep time. Right? Now, you know, when we look back on that, it's like, well, yeah, but throughout the day, the clock's going to run progressively slower. Once that spring runs out, okay, the clock is going to run progressively slower because it's not going to swing through that full arc anymore. Yeah?
Is that like what metronomes use? Like when you line them up in the 90s?
Yeah, exactly. They have a little spring inside. When you pull them away, that spring will keep them going back and forth. Then they eventually quit. Yeah. Okay, but I mean, they keep the beat for long enough for you to practice your song or whatever and then try it again. Yeah. Okay, making some sense? All right. So, like we said here, for a mass on a spring, the two things that can affect the period of a mass on a spring are the mass you put on the spring and the stiffness of the spring. Right? So if I want to calculate the period of a mass on a spring, this is the formula I would use. T equals 2 pi times the square root of m over k. So if I need to manipulate this equation in order to solve for m or k, what do I have to do to everything in the equation? Square it. Yeah. If I'm going to move something out from underneath that radical, okay, then I have to square everything in the equation so that the radical disappears. All right, so before I can manipulate this, I would have to convert it to this. Then I could manipulate. Okay? After that, is it very hard? Okay. As long as I remember to square everything, it's a pretty easy formula to use. Okay? So what this means is greater mass means greater period. Okay? If I put more mass on the spring is going to take longer to make a full oscillation because that spring is going to have to pull on more mass. It's going to take it longer to slow it down and stop it, and then it's going to go past equilibrium further in the other direction. Okay? If I get a stiffer spring, that'll actually make the period go down because a stiffer spring will oscillate more quickly. Okay? Go back to the idea I used before, where if I had the spring out of a little clicker ballpoint pen versus the spring from a car. Okay? If I just hung a mass on each one of those and went like this, okay, my car spring would like oscillate barely at all, and the pen spring would go way up and down, way up and down. Okay? Or if you had like an elastic band and the kind of bungee cord used to bungee jump with. Okay, those are springs as well. Okay, if I hung, a person off of each one of those, it would probably break the rubber band. Okay, but the bungee cord would hardly oscillate at all. Okay, so if I want to use that formula, let's just use it to solve for the period of a 0.2 kilogram mass attached to a spring with a spring's constant of 28 newtons per meter. Okay, so we're looking for period. We know the mass and we know the spring's constant. Okay, so if I want to find period, I just have to plug in the numbers. Okay, so I go 2 pi times the square root of 0.2 divided by 28. Okay, and I would get that that particular mass on the spring would take 0.53 seconds to complete one oscillation. Now, what if the question asks for the frequency? If I know the period, can I calculate the frequency? They're the inverse of each other. Okay, so if I wanted to solve for f, f is 1 over t. So I would just go 1 over 0.53, and I would have the number of oscillations per second, okay? Because period is seconds per oscillation. Okay, frequency is oscillations per second, or hertz. Okay. So this formula we learned in Unit 3 and used once. Now we're going to use that formula all the time. Okay, period and frequency get used all the time in simple harmonic motion and waves. Okay. All right, questions on that first mass on the spring question? All right, then for the pendulum, okay, the period is 2 pi times the root of L over G. Okay, so it looks like that on your formula sheet. Okay, big T is 2 pi times the root of L over G. So once again, if I want to solve for anything under the radical, okay, then I have to square everything. Okay, so a longer pendulum, bigger period or smaller period? Bigger, yeah, okay. L is on top, right? So if L gets bigger, T gets bigger. Okay, greater gravity? Gravity gets greater, smaller period. Okay, when you think about this, guys, on Earth, okay, this pendulum swings like this. Okay, if I was on Jupiter, okay, where the acceleration due to gravity was a lot further, would it swing as far? It would make like really, really short oscillations back and forth like this. Okay, that would have a much shorter period, okay, than it would on Earth. Okay, so if I have a simple pendulum here, okay, with a length of 1.55 meters at a high altitude where gravity was only 9.71 meters per second squared, I can calculate the period of that pendulum by simply plugging those numbers in. 2 pi times the square root of 1.55 over 9.71, and I would get that that pendulum takes 2.51 seconds, okay, to make one complete oscillation. This one isn't quite 1.5 meters, okay, probably closer to 1 meter, maybe a little more than 1 meter. Yeah, probably takes about 2 seconds to make a full oscillation. Okay. In a grandfather clock, how long do you want the period to be? Yeah. Either 1 second or 2 seconds. Either you want it to be clicking every other one, okay, or on each side. Okay, one or the other. All right. Now, terminology here. So the mass on the end of the pendulum has a name. Anyone know what it is? Bob. Okay, the mass on the end of the pendulum is called the bob. Okay, so I don't know why that is, it's just called the bob. Okay, so anytime you're dealing with a pendulum, you are dealing with pendulum bob squarepants. Plumb bob squarepants. Pendulum bob. Okay, that's what that thing is called at the end. Pendulum bob. Okay, you can always remember that because you can sing the song to yourself in your head. You know, if you live in a pineapple under the sea, absorbent porous and yellow as heat. Yeah. You're gonna have that in your head. You're welcome. Apparently, you get dumber by watching that show. You ever heard of that one? Apparently, that's like the case. You actually get dumber by watching that show. So, yeah, don't watch that show. Okay, I would like you guys to try this one here. Okay, see if you can determine the length of a pendulum that would have 1 second here on Earth, where gravity is 9.81. All right, so for this one here, okay, they told us the period, okay, 1 second. And they told us the acceleration due to gravity, 9.81 meters per second squared, okay, and we are simply looking for L. So if T equals 2 pi times the root of L over G, the first thing I have to do is square everything to get rid of the root. So T squared equals 4 pi squared times L over G. Then I multiply both sides by G, divide both sides by 4 pi squared, and I'm left with L. Okay, so 1 squared times 9.81 divided by 4 pi squared. Okay. So should give me 0.248 meters, so roughly 25 centimeters. Okay. Everybody all right with that? Is this a terribly hard formula to use? Is the one for the mass on a spring pretty much the same thing? Yeah, it's just instead of L and G, it's M and K, but the manipulation stuff is the same. Okay. All right. Try that one. Solve for G. All right, so on this one here, we're told the length of the pendulum, okay, 0.65 meters. Okay, the period of the pendulum is 2.8 seconds. We're looking for the acceleration due to gravity. So T equals 2 pi times the root of L over G. And so T squared equals 4 pi squared times L over G. And then we'll just swap T squared for G. And so G will equal 4 pi squared times 0.65 divided by 2.8 squared. Okay, so we're looking at an acceleration due to gravity of 3.3 meters per second squared. What planet would that be? Which planet in our solar system has 1/3 the gravity of Earth? Mars. Okay. We're looking at that pendulum being swinging back and forth on Mars. Okay, that's really all there is to pendulum and mass on spring questions, is just being able to do what we've done there. Square everything, move stuff around, perform algebra. You're not going to be setting that equal to anything else. Okay, it's just as simple as it sounds. Okay, it's just a matter of understanding what you're looking for and what you're being given in any particular question. Okay, so this one, just a quick review of this formula. Okay, T equals 1 over F. So if an automobile engine has its pistons oscillate up and down, okay, with a period of 0.0625 seconds, how would I get the frequency? T is 1 over F. F is 1 over T. Okay, so if I go 1 over 0.0625, okay, 16 hertz. That means an automobile engine revving at that rate, okay, the piston goes up and down 16 times per second. Okay. Everybody all right with that? We can't do that one yet. And we can't do those yet because we haven't done them. Okay, but you can do that one. Okay, give that one a try. Without using the formula from last unit. Use one of the formulas we learned today. You should be able to calculate that. Is that gravitational field strength, little g? Yes, it is. Remember, in the last unit, boy, I hope you remember, we learned this formula for calculating gravitational field strength. Little g is gravitational field strength. Okay, I'm not going to use that formula right now. Okay, but I can use this one. Because I have the length of the pendulum and the period of the pendulum, and gravitational field strength is in that formula, little g. Okay, so that's going to mean g is going to be 4 pi squared times L over t squared when I manipulate all that out. So 4 pi squared times 1 meter, okay, divided by 2.01 seconds. Oh, what I messed up there. What did I mess up? Oh, I forgot to square it. That's, yeah, because it came out to be twice what it should have been. Yeah, I forgot to square it. Okay, so this number divided by 2.01 squared, which happens to be just about double. There we go, 9.77. Okay, is that a reasonable answer? On a test, were you to do what I just did and screw up and look at that, would you know you'd done it wrong like I did? Yes, because that was a completely unreasonable answer. Going to the top of Mount Everest does not make you 2 times heavier. Okay? All right. All right, let's have you try those 3 there. Okay, they are all pendulum questions, and then we'll get to a few mass on the spring questions after that.